And all I know which ones are these ones.
Are y'all ready? Hello? Hi. I'll pass the exams back towards the end of class. We've got chapter 12 left to cover before the final. 12.1, 12.2, and 12.3. So we'll start out with parametric equations, then polar coordinates, and then calculus and polar coordinates. If you have to go on to Calc 3, there are some instances where you do have to look at parametric equations. They're useful for describing like trajectories. Although we don't get into a great deal of detail with them, you will see them at least a little bit again in Calc 3. The idea here in 12.1, here's kind of what we're used to with this standard input output kind of thing. Y is a function of x. So what we're going to look at here is a parameter that's called t, or typically labeled as t. This is our parameter. And a function of g gives us the x coordinate, and a function of h gives us the y coordinate. So it's just another way, an alternative way to explain or describe functions that we've seen up to this point, y equals to f of x. There's alluded to here in chapter 12 is different coordinate system, which you might have seen a little bit in pre-calculus, which is the polar coordinate system. In Calc 3, you also look at spherical coordinate systems and polar coordinate systems, and what else? Circular coordinate systems, I don't know. There's 3 different coordinate systems that we end up looking at the end of, by the end of Calc 3. So although when we parameterize a curve or a function, it doesn't give us a new coordinate system. It does just give us an alternative way to describe that. Okay, so we're essentially describing the point xy as a function of t. So x would be given to us by g of t, and y would be given by some other function of t. And like a general thing, you would have these two coordinates like x of t defined by some function of t. I don't know, let's say it's 2t plus 1, and y of t, let's say, I don't know, it's t squared, for example. And then you're given some restriction. T is in between 0 and 1, let's say. So that's an example of a parametric equation. A lot of this section is really devoted to kind of getting your bearings with parametric equations, and then it builds up with how do we take derivatives when functions are represented parametrically, and we do also look at arc length. So how do we measure the length of a curve that's described parametrically? The thing with these parametric equations that we didn't have with our standard y equals f of x is we have this forward or positive orientation. And we'll see, we'll plot a couple of these. But for instance, as t ranges from like 0 to 1, this set of points or this curve that's generated by x and y, you see unfolds in a very particular way. So as t increases from 0 to 1 or from A to B or wherever, the direction that curve unfolds as t increases is called the positive or the forward orientation. Also, unless t is not restricted, we do have initial points, like the first point on the graph that's generated, and a terminal point, which would be the last point. So for here, like when t equals to 0, that would give us our initial point. And when t equals 1 would give us our terminal point. So there is a little bit of difference, although it describes the same sort of functions or curves or whatever. Typically, when T is restricted, they have initial and terminal points, and it also has a specific direction in which it unfolds, whatever that looks like. Okay, so an example of putting all of that together. So we have x is defined as cosine, y is sine of t, and t is in between 0 and 2 pi. So we're going to make a table of values. We're going to plot the points from the table. We're going to then eliminate a parameter, which means t, from the parametric representation to obtain a Cartesian representation in terms of x and y, and then describe the curve. So part A, our input is really t. So I'll just kind of do this. We'll have t as a result of t, we'll get x and y. And since we're dealing with sine and cosine, let's just pick a few points that we know the value of sine and cosine, and then so we can just fill in the rest of the points implicitly. So let's do 0, pi over 2. 3 pi over 2 pi and 2 pi. So we're going to plug those values of t in for x and or in for t and get x and y. So we have x is the cosine of 0, which is 1. Y is the sine of 0, which is 0. So that point we get when t equals 0 is 1, 0. Yeah.
3 pi over 2.
Huh?
3 pi over 2.
Yeah. All right, so since that was our starting value of t at 0, that is our initial point. So then as we increase t, the points that we get subsequent are going to, in effect, show us how the curve unfolds or give us the positive or forward orientation. Okay. Pi over 2, cosine of pi over 2, sine of pi over 2. So that gives us the point 0, 1. Cosine of 3 pi over 2. That's cosine. Cosine of 3 pi over 2. That's 0. 0, negative 1, sine of 3 pi over 2. So it does have a specific direction, if you will. We're following this direction from the initial point to the terminal point. Cosine of pi, negative 1. Sine of pi, 0. Negative 1, 0. And then cosine of 2 pi, sine of 2 pi. So you see the ending point when t is 2 pi is the exact same thing as the starting point. So we start at 1, 0, we end at 1, 0. Okay, so part B says, plot the points in the table and the full parametric curve, indicating the positive orientation. So we got our initial point at 1, 0. I'll just label that initial point. Then we come to 0, 1. Notice we have all of these other values in between, though, that we didn't plot. So all of these values in between will give us something in between these 2 points. We've got 0, negative 1. And then negative 1, 0, negative 1. Sorry, that's down here. Negative 1, 0. Okay, so what does it look like we're going to get here? Okay, so we get a circle. What's the radius? 1, yeah, because all these points are 1. This is consequently our terminal point as well, and our terminal point. So we went, sorry, my points were out of order. The circle's gonna move that too. Okay, so we're just gonna draw those arrows to indicate positive orientation. It's counterclockwise, starting at the point 1, 0. So it's circle, radius 1, traversed counterclockwise direction with the initial point of 1, 0. All right, so does anyone have any questions on that? Yeah.
Why then did we go 3 pi over 2 and then pi?
Yeah.
Pi over 2?
Yeah, just
Yeah.
so we have negative 1, 0. Okay.
So for B, by putting those arrows in there, you're indicating the direction of possible orientation.
By say that again. By
Putting those arrows in there.
oh right, yeah,
Indicate
yeah,
the positive. That's what that.
yeah. That's indicating the positive or the forward direction.
The forward direction.
Okay, part C, eliminate a parameter, T. So that we want to take this representation of parametric and then represent that as a Cartesian. Any ideas? Yeah, we kind of already know what it is, right? So what would we need to do here? Yeah. So how do we get that from this? Yeah. So remember the identity sine squared plus cosine squared is equal to 1. Okay, well sine squared is y squared plus x squared equals 1. Okay. That's really all we had to do was just square both sides. I mean, we already knew what it is, but it's important to be able to convert or to change from one to the other. Sometimes you might not know what it is unless you went through this process of plotting points, and it's kind of tedious sometimes. Okay, so there we have our Cartesian representation, and then in part D we just describe the curve. Circle center of 0, 0 with a radius of 1. I guess positive orientation. Positive orientation counterclockwise with initial point of 1, 0. All right, questions on that? Yeah.
You say positive orientation counterclockwise. Are you implying that the counterclockwise direction is the positive direction? Or are you just saying it is going positive counterclockwise?
Yeah, that's typically the here what we mean when we say positive orientation. It's a little more descriptive as well, saying this is our initial point, so we're starting here, and as t increases, as our parameter increases from 0 to 2 pi, the circle is generated like this. It stops there.
So counterclockwise is not necessarily the going to be positive direction of rotation.
No.
For this scenario.
For this one, right, right. In fact, if we said that y is sine of t and x is cosine of t, we would still get a circle of radius 1, but we see that's clockwise. Yeah. We can see this. There might be other ways to plot this in Desmos, but we're gonna like pretend you're gonna plot a point, but the x coordinate is cosine t, and the y coordinate is sine of t. So if t ranges from 0 to 2 pi, then we can see. But that's a static image. If we want to see how that actually unfolds, then we've got to put this little bracket. Say that t is less than or equal to something else. You should ask for a slider. I don't know. Oh, we got to put this inside. So there might be a better way to do this. I just haven't really messed with it a whole lot. So let me choose that slider for A. We'll say A goes from 0 to. And so then when we slide A, you can kind of see how this actually unfolds. So that's our positive orientation. All right, same thing with this parametric equation. So I'll give that a shot.
So like on the triangle.
Well, my son needs goggles. I was like, you don't sell them. She's like, that's what you should sell them. And I'm like, I was like,
Maybe I don't usually have enough weight, I don't know. Like weight always has to be even weight.
you know,
Did y'all get at least that far? Yeah. Okay. Part C, did y'all finish that? So this one wasn't too bad. X is t and y is t squared. So that means we're just going to plug in t equals x for this right here. So we get y equals x squared. That's our Cartesian. Notice it's not, since we restricted t, it's not the complete parabola, right? It's blocked off from -2 to 2. And then so part D, parabola. Yeah, vertex. Vertex is 0, 0. And you know, the positive orientation from left to right, I think that's good enough.
I wrote concave up.
Yeah. So if it's concave up, you know, we could have the positive orientation going from left to, or sorry, right to left.
say positive left or right.
Yeah.
So is this what you mean when it works with trajectories? Say that was flipped upside down, you can calculate
Yeah.
which direction something.
Right. It's like, you know, this thing is going this way. Whatever. Very simple. Right. Yeah, I mean, to be more specific, we could say that, you know, it's concave up, parabola is opening up, positive y direction, whatever. Be more descriptive. if you need to be. Any questions on that? So again, it's just kind of get us into the habit of working with these, and just to verify that they do describe, you know, normal types of functions or relationships. We have one more example, and we'll talk about circles. So this, I'll just write down the table. I think that's kind of hopefully straightforward. -2 to 1. So this is our, since t is -2, starts at the leftmost point. This is our initial point, whatever we get here for x, y. 2, -5 is our initial point. We'll just fill the rest of these in. -1, 0, -3, 0, 0, -1, 1, 2, 1. Stop at 1, that's our terminal point. Terminal point.
Plus
2, -5. Let's just say that's there. 2, -5. So that's our initial point. Start there. Then we go to the point 0, -3. Somewhere there. 0, -1. Here. And 2, 1. So that's right there. I'm gonna skip that one down a little. So, do we know what that is?
Looks like sideways parabola.
Yeah, looks maybe like a sideways parabola. One way we could fix that is just to pick more values of t in between -2 and 1. Plot those. So maybe at this point we would say, well, I need a few more of these values because I don't quite know what this is going to be. But we can maybe look at part C to kind of help us with that. So eliminate the parameter. T squared plus t. And it's 2t minus 1. So yeah, there's really two choices here. We could take two different routes. I could take the equation for x and solve that, and then plug in for the equation of y, or I could take the equation for y, solve for t, and then plug that back into the equation for x. Suppose we could look at both of these. So we could take this equation, solve for t, and plug in y equals 2t minus 1. So we'll do that one first, and then we'll do the I guess the opposite. Take y, solve for t, plug into x. So x equals t squared plus t. How do we solve that for t? Yeah, for the in x equals t squared plus t. Yeah, so notice if we factor it though, so does that work to do that? So say x is 2, how many solutions to 2 equals t times t plus 1? Really? 2? How many numbers can we think of that can multiply to give us 2? Yeah, well, they have to be 1 apart, but how many of those types of things could we construct? There's not just 2, right? If this is 0, then there's only 2. Either this is 0 or this is 0. If this is 2 or 10 or 150, there's infinitely many numbers we could come up with that would give us that, which is why we don't set quadratics equal to numbers. So yeah, you've got to, it's quadratic in t. You have to set it equal to 0 and solve for t that way, either by factoring or by the quadratic formula. You're right, yeah. So there's 2 ways to do this, like we said. We're going to do it this way, and then we'll do it the other way, where we solve y equals 2t minus 1 for t, and then plug that in for x. So let's say quadratic formula with a equal to 1, b equal to 1, and c equal to negative x. So we have t is the opposite of b, plus or minus the square root of b squared minus 4 times a times c all over 2a. So we've got what t is. Now we're going to plug that into y equals to 2t plus 1. Do what? Oh. Okay, well, hopefully you see what happens. The 2's cancel out. This 2 divides this 2. So we just have negative 1 plus the root, plus or minus the root, rather. Minus this one. Or we could say minus 2. Now, granted, that's not typically what we're used to seeing in terms of a Cartesian equation, but maybe it's a little bit better than seeing like x equals to y squared plus y plus something else, right? Because if you can remember what the square root graph looks like, we've got a positive root and a negative root. So if we think back to this, our crummy graph that had those 4 points on it. And if we think about a positive root, a positive square root maybe looks something like this. The negative square root looks something like that, right? So I don't know if that's any better to look at an equation like that. So let's try it the other way. Let's then take the equation for y, plug that into x after we solve for t. Do it that way. Okay, so t is also y plus 1 over 2. Plugging that into x equals to y plus 1 over 2 squared plus y plus 1 over 2. So t squared plus t. So maybe you could like simplify that a little bit. It is a quadratic in y because we have a y squared y. But I don't know if that lends itself any better to the actual graph. So you can expand all that stuff out, combine like terms. 1/4 y squared plus y plus 3/4. Quadratic in y. But I think we're maybe even less familiar with graphs like that. It is a parabola that opens in a positive x direction. But maybe at least with this representation, we could find the vertex of the parabola. If we just graph that in the Cartesian coordinate system, it's just a parabola that opens to the right. Is everybody okay with that? Somewhat familiar? Okay. So it doesn't matter which one you actually look at, the one for y we have above or the one for x. They're going to give you the exact same graph. What's the vertex of this one? I'll just remind you, negative b over 2a, and then you plug in the function. Call it f. We have negative 1 over 2 times a fourth. So the coordinate there, negative 2, and then we'll plug that back into the 1/4 y squared plus y plus 3/4, and then that would give us this vertex here. We didn't quite get that when we did part B. So our vertex is somewhere in here. But maybe after we've looked at those two, we could sort of see that we start here, and then we sort of go this way. I didn't draw that very well. With this orientation. Stopping. So it's supposed to be more of a U-shaped than it is an L, but that's the idea. Yeah, you can find more points in the table. If they want all of this other stuff, you know, might be easier to look at one of these. I don't know. But yeah, certainly you could plot more points. Sort of what you do with these though, you just like with regular graphs, you end up moving away. Like if someone says, hey, graph sine or cosine, like you know how to just draw that out, right? You don't have to plot points. So that's kind of the point of part C in all of these. It's like if I don't recognize this parametric curve, is there a way I can sort of translate that back to the Cartesian system? And then maybe that's something I can recognize. Any other questions on this? And these representations are not unique. So for instance, the equation y equals to 2x minus 12, all of us could come up with a different parametric representation for the same line. Here are just a few. If I say x is equal to t, and most of them are obvious once you see like a substitution kind of thing. So if x is t, then y is 2t minus 12. I guess some other ones we could continue in the same vein. If x is t squared, then we would let y equal to 2t squared minus 12. That's also the line 2x minus 12. Maybe a third one. If x is 3t plus 4, then y would have to be 2 times 3t plus 4. And so on and so on, we can continue. Those are all substitution based. Surely there's other types of ones too. So these parametric representations are not unique. Okay, as far as circles with parametric representations, let's just say maybe this is, first of all, this is like a function of x, and then we'll talk about the parametric ones. Just to kind of remind ourselves what A, B, C, and D are in sort of a general trig sense. What was the value of A? What did that give us, or tell us, or do? Is what? Yeah, so that's the, and the parametric or the polar representation that's related to our radius, but just from a Cartesian sense, that's our amplitude. What did B do for us? Yeah. Period. Sine and cosine's period was 2 pi, so the period is 2 pi over B. And if you think about taking sine from 0 to 2 pi, and then wrapping that around, is what we get. So if I start affecting this period in the sense of a circle, what do you think that's going to affect? Not the radius. It won't affect the circularity of it. When it's drawn? In what direction? So not necessarily what direction. How it's drawn is more accurate. As a, say that again, the time it takes to draw the whole. Right. So how much of the circle is generated? If this is 1, right, it's just the sine of t minus c. We have a full circle generated after 2 pi units, right? But if this is the sine of 2 times t, then we have a full circle generated in pi units. We'll just make note of that, but it does affect how much of the circle is given. For parametric equations, we don't see this c right here, but in terms of a Cartesian, what did that do for us? Yeah, that was they call that the phase shift. For us, that part is not present in parametric equations of circles. And then what does D do? Right. And then D is your vertical. Up or down. for, now we'll note here, this is for a parametric. So let's just say we're dealing with x equals to a cosine b, cosine of b times t plus c. I guess no, we'll call that d, so it corresponds with d above. C was inside the right there. Plus d. Yeah, c is 0. And y, let's do lowercase a sine lowercase plus lowercase. And primarily what we see, this is a circle if lowercase and uppercase a are the same. I should say absolute value. As we'll see in a minute, doesn't matter what that sign is, positive or negative. But if those two a's are the same number, then you have a circle. If a is different from lowercase a, then you've got something else. Could be an ellipse, could be
And say with B.
Hmm?
And say with B when you said A.
yeah, a and circle.
What if the B's are different?
So we can look at that. We don't encounter that either. Yeah. So that's typically how we see a circle come up. I will make a note for us. B is also equal to lowercase b. Okay, remember that b affects the period. That affects how much of the circle is actually traced out as t ranges from whatever s to w. Okay, so this b and this b tell us how much of the circle. So we said D was up and down depending on the sign of D. Those don't necessarily have to be the same, but what they affect is, if you can imagine that this is a circle, if we're going to move that up, down, left, right, according to left, right, x rather, and up, down according to y, that the capital D and the lowercase d would affect the center of the circle. That's our kind of this, vertical, horizontal translation stuff. Okay, so the D's affect the center. Someone said it already, the A is the radius. The radius is the magnitude of A. Okay, so that's a parametric representation of the circle. We'll look at a few examples and also talk about how we convert that into a Cartesian system. So note here, if B or B is positive, then we get a circle like we saw in that first example, generated positive orientation in the counterclockwise direction. So that was, we saw that directly from the first example. If B is negative, then you've got a positive orientation of clockwise. Do you have any questions? It's all very generic at this point. What if, so if we had instead x equals to sine a sine b of t plus d, y equals to capital A cosine b of t plus t. So here, what would be different as opposed to what we had earlier? The initial point would change and the orientation, the positive orientation would change. A is the absolute value of A is still the radius. B, same numbers affecting how much of the circle you get. The center is now lowercase d, comma uppercase d. We can write all this stuff now. The circle, again, if A is equal to A, radius A, center d, comma d, x, y. What else did we say? B still affects the period, so B is still how much of the circle. So this time if B is positive, then the positive orientation is clockwise. We just kind of switch the role. Sine, cosine switches the orientation. And the initial point. Similarly, if B is negative, then the positive orientation is counterclockwise. You'll have what you need. No, that's a lot of information, but here's an example. If x is 12 cosine of 2t and y is 12 sine of 2t, what are we actually looking at there? What does this parametric representation give us? A circle. All right. There's no what?
There's no D, so there's 0, 0.
Right. So it's not anything plus or minus out here. So the center is at 0, 0. Okay, what's the radius of the circle? 12. From this number here, that's our A. I guess we want to know perhaps how much of the circle do we get here? Which would give you, okay. So yeah, there's a, remember this b right here is affecting the period. Sine and cosine's period are 2 pi, so the period. No, because the period of sine and cosine is 2 pi. And remember the period is 2 pi over the absolute value of b. So one full circle is generated every pi revolutions. And since we're going from 0 to 2 pi, we get 2 circles. So the period is, yeah, the period is pi, which means we get a complete circle. Pi revolutions, I guess. We got to look at t though. T ranges from 0 to 2 pi. So when t goes from 0 to pi, we have one circle, and then from pi to 2 pi is another circle. So we actually get 2 circles here. So since t is in between 0 and 2 pi, the parametric equation generates 2 circles. Centered at 0, 0, with radius of 12. So naturally, when you look at the graph, it's just going to be a circle. But really what's happened is that circle's been traced out twice. The other way to see that, I think, perhaps that's just as easy, if not easier, is we look at the argument for sine and cosine, which is 2t, right? T ranges from 0 to 2 pi. So like if I look at, maybe here, when t equals to 0 and t equals to 2 pi, when t is 0, 2t will be 0, so that's kind of the starting value. And when t is 2 pi, we have, sorry, I'll write this. I just want to be a little bit more descriptive here. And when t equals to 2 pi, we'll have cosine of 4 pi and sine of 4 pi. So what we're going to do is look at the arguments when t is 0 and t is 2 pi. And then we see that that ranges from a cosine value of 0 to a cosine value of 4. Right? Is that helpful to see that there's actually 2 circles there? So that's another way you can think about it. But it is just like a straight determine the period problem and then look at where t ranges from. Because if t just ranged from 0 to pi, that's fine. You would only get 1 circle. But since it goes from 0 to 2 pi, we get 2 circles. If it goes to 4 pi, you get 4 circles, and so forth. Actually, I guess I should have left some more room. Well, I mean that's pretty much it. We can describe it that way. But how do we turn that into a Cartesian? Yeah, let's say we forgot. Let's say I forgot that's a circle radius 12, center at 0, 0. If I'm on the exam and I'm looking at that and I'm like, oh, I have no idea what that is. How could we have an idea of what that is? Yeah. So before we go squaring cosine and sine of 2t, let's divide both sides by 12. So we have x over 12 is cosine 2t. And also y over 12 is sine of 2t. Now we can square sine and cosine to get to fit that into our Cartesian, because we know sine squared plus cosine squared of whatever, theta 2t 35w, is that those are always equal to 1 when they're squared and added. Yeah, so we have sine squared of 2t plus cosine squared 2t equals 1. But sine squared of 2t is y squared over 144. Cosine squared of 2t is x squared over 144. Okay. Is that all right? So if we forgot what this is, maybe at least we'll think, hey, square sine and cosine, see what happens. And I know that this is multiplying both sides by 144, rearranging x squared plus y squared equals 144. Circle center 0, 0, radius square root of 144. That's how we manipulate that. Do you have any questions? So that's our x, this is our y. And what we didn't get with saying, oh, that's a circle centered here, radius this, we didn't actually mention what the positive orientation was. So what is the positive orientation for this circle? Yeah, how do we know it's counterclockwise? Because b is greater than 0, x is cosine y sine. So positive orientation is counterclockwise. Let's see if we get that. There's our circle starting generated counterclockwise. See right at 3.14, we've got a whole circle. And then as we continue, we don't see it, but we are tracing the other circle. We have 2 circles there. Any questions? So we'll take a break and then continue. For that to be like a motivational speech or anything, but
I always felt like the quality of instructors who did it, like junior colleges or junior colleges, are way more.
absolutely. Yeah, I have the same experience for me as well. So I honestly missed community college when I left because I'm like, man, these teachers at the university, they don't care, man. They're up here.
I was just going to say, my tutor was in that Patriot C folder. She was looking at a lot of the work we've done here, and she said it's actually a little more advanced than what they're doing.
Oh, really? Okay.
Yeah, it could be just because she was like graduated 4 years ago, but still, you know.
Yeah. I've seen somebody's calc exam from USCU Boulder, and it was a Calc 1 exam, and it looked pretty brutal.
Oh, did
Yeah.
Okay.
So yeah, maybe it depends on the professor. I don't know.
Like better or worse than Gonzalez?
I don't know. I've seen his exams. His exams look pretty tough.
Okay.
Yeah.
Not to be the program, but no, I'm trying to go to see Boulder. So if I run to that professor, I'll try to tell him that. Mr. Fisher, politely tells you to eat a dick.
He'll say, oh, that dude has a master's degree. He's an idiot.
Yeah.
All right. So how about 12 cosine of 2t minus 1 for x and 12 sine 2t plus 3 for y? What are we looking at there? Okay, we've got another circle. Center at negative 1, 3. Do y'all agree? We have our x shifted down 1 unit, y shifted up 1 unit. Radius again of 12. What's the orientation? Yeah, positive orientation, I should say, is counterclockwise because we have x as cosine, y as sine, and b is positive. So b is positive, x is cosine, t, y is sine. So anytime you have x being cosine, y being sine, and b positive, you will get a counterclockwise positive orientation. Positive orientation.
Did I say cosine of t or cosine of x?
Cosine of t, I need to, originally was thinking of x, but let's see. Right, yeah. So how much of the circle we get, is it half a circle? Do y'all agree with that? I mean, there's two ways to look at this. The period of sine and cosine is 2 pi divided by our b, which is 2, gives us a period of pi, but t is only ranging from 0 to pi over 2. So one circle is generated every pi revolutions, but we're only doing half of that with pi over 2. So we're only getting half of the circle. Remember the other way, or we could think about it like this. Our argument still is 2t. So we're basically looking at cosine of 2 times 0, sine, sine of 2 times 0 for the initial point or initial value. And then we're going all the way to the cosine of 2 times pi over 2, and the sine of 2 times pi over 2. So we're going from cosine sine of 0 to cosine sine of pi. We know when we graph cosine and sine from 0 to pi, we only get half a circle going from 0 to pi. So you can look at that either way. It doesn't, I really don't care. Now again, if we forgot that, how do we take this equation and convert it? So we think about squaring stuff, but we want the sine and the cosine by themselves before we square that to use the Pythagorean identity there. So we need to first isolate sine and cosine. Dang it. So we have x, we're going to add 1 to x, and then divide by 12. Equals cosine of 2t. Same thing with y, we're going to subtract 3 and divide by 12. And then so putting that together, we have cosine squared plus sine squared equals 1. In other words, x plus 1 over 12 quantity squared plus y minus 3 over 12 quantity squared.
Well, that's one, 1/12 square.
Yeah, 1/12 squared. So we've got x plus 1 squared plus y minus 3 squared. We're going to multiply through by 12 squared to get rid of the 1 over 12 squared. So although that's kind of sufficient to get our bearings and say, okay, well, I'm looking at an equation that describes a circle of center -1, 3 with a radius of 12, that doesn't tell us anything about the orientation or the initial and terminal points. So it's kind of like part of the story if we're able to do that. But at least we have our bearings as to what we're dealing with. Yeah.
Why go positive?
Oh, well, we had to subtract 3 to the
I thought
y.
you only did that with X.
All right. Yeah, any other questions about that? Next example, similar. Describe the circle. So what's the center of our circle here? 1, 2. Radius. 3, what do y'all think? We have the radius is the absolute value of that radius 3. What else do we want to know? What's the positive orientation? Counterclockwise, do y'all agree? Yeah. So we have our b is actually what? 4 pi is our b. Still positive b, 4 pi is positive. Counterclockwise. How much of the circle do we get? Do what? 1 full circle. Do y'all agree with that? Okay, so our period is 2 pi over 4 pi. And then t is ranging from 0 to a half. So here, let's look at it this way. Period. When t is equal to 0, I'm just going to look at this part, cosine of 0. And then when t is equal to 1/2, the x part, again, is cosine of 4 pi over 2. So as t varies from 0 to 1/2, the argument of sine and cosine ranges from 0 to 2 pi. So you get 1 full circle. Is that okay to think of it that way? Do you have any questions on that? Of course, we would have this. You know, we would have the 1 minus 3 cosine. We have 1 minus 3 sine of 0. But it's all the same. Cosine and sine range from 0 to 2 pi, so we get 1 circle. The conversion is identical to what we did in that last example. Any questions on that? Does that make sense? The next example has us find a parametric equation for a circle centered at 2, -4 with a radius of 3/2, generated counterclockwise. Remember, there's 2 ways to do that. X cosine, y is sine with a positive b, or x is sine, cosine is y with a negative b. So I would try to set this up initially in the most straightforward way, and then see if that matches with the initial point. And from there, we can manipulate if we have to. So let's just take this information, a circle centered at 2, -4, with a radius of 3/2, and write out the equation for that, and then we'll see how to fit that initial point in. So we need to describe both x and y. So a circle with that criteria, what would it look like? X equals, y equals. So here's where I would just think of the most basic situation and then try to fit in the initial point afterwards. So let's just do cosine of t. And then how do we account for the center? +2. And then y would be what? Okay, good. 3/2 sine t -4.
If you're going counterclockwise,
Yeah. Just greater than 0, yeah. So here our b would be 1, which would generate it in a counterclockwise fashion. Yeah, yeah. B could be anything greater than 0, but we have to make sure that this b is giving us an initial point of 7/2, -4. So we have to determine, we have to now determine t ranges between what and what. We have to determine that. So like I said, I would just start off with these things pretty basically. 0 to 2 pi. Get a full circle, because my argument is from 0 to 2 pi. And let's just see if that gives us an initial point when t equals to 0, since we're starting at 0. I mean, it's really ambiguous at this point. We could say, well, couldn't t range from like -2 pi to 0 or anything thereof, right? So there's really so many choices for this. Start out with the most basic one and see if it works. So if t equals to 0, then what do we get for x? Yeah, we have cosine of 0, which gives us 1, so we have 3/2 plus 4/2. 7/2. If t equals 0, y equals -4. Okay, so that's it. I mean, we stumbled upon that, but we just kept it very basic. That's kind of how I'd recommend approaching these. Not like you see a lot of these because they can be very ambiguous. But that's it. That's our equation.
so
Oops.
we really must choose, I guess,
Yeah. Right. So really we have this b here, and I want to say that b of t when t equals, if I said, let me do this from, let's let t range from pi to 3 pi. Then we would have to do some, it would give us, because the sine of pi, the sine of pi is 0. Okay, so yeah, that would give us,
that'd give us
yeah, our initial point would our initial point change? Yeah, because it would be a negative 3/2. Okay. But if we said maybe let's start there, then we have to look at this equation and start figuring out what do we have to manipulate so that if I start t at pi and end at 3 pi, x initially comes out to be 7/2 and y initially comes out to be -4. It's not straightforward.
So would it tell you if it wants multiple circles or if it just says a circle, assume that it's just one revolution?
Yeah. So it would specify. Let me do another one. This would also work if x is -3/2 cosine t plus 2, and y were 3/2 sine of t minus 4, and t ranges from pi to 3 pi. It would also work. I think it's a lot less natural than the one we started with, but there's many other things that would work too. Yeah, I would say so.
It seemed like you moved the constraints and it still works.
Yeah, because you could always find these numbers here. Like, and we could put a b in there if we needed to. All right. I think we'll skip the next few examples because we've kind of already seen conversion of this here. We've looked at 2 examples of how to convert that. Converting something like this we saw with our first example. Do y'all want me to write down the answers if you want to look at these later? Okay. So the I'm gonna go up here, the circle. Circle radius 3, center -4, 2. We have x plus 4 squared plus y minus 2 squared equals to 9. For that one.
I do have a question for those.
Yeah.
So do we just kind of assume that t goes from negative to any number in there? Do we need to care about the fact it didn't give us a bound for t?
Yeah, because the only thing the parameter restriction or no restriction would be the amount of the circle we get. Either way, if we talk about a quarter of that circle or 12 of them, the equation in Cartesian sense is still the same. So this one, we get, I guess it depends on what route we take. If we take x and solve for t, plug that into y. So solve x equal t minus 3 for t, and then plug that into y. You should come up with y equals to 2x plus 10. So we see this parametric equation represents that line, or part of that line rather. Or we could take the other route, we could solve y. For t, and then plug that in into x. We get x equals to 1/2 of y minus 4 minus 3. Either way, we're looking at mx plus b, restricted from 0 to 2, so you get part of that line. Same kind of thing, eliminate the parameter. Should be able to come up with y equals to the quantity, x plus 4 squared. Notice here t is all real numbers, so we would actually generate that entire parabola with that particular equation. So that's x plus 4 squared equals y. We can look at this one because this is different. Notice we have different a's here. T ranges from 0 to pi. So eliminate the parameter and find the Cartesian equation and graph it. So this is it's kind of the same idea though. It's not a circle because the a's aren't the same, but the process is similar. We're gonna isolate the sine and the cosine. So we have x over 2 is cosine, y over 3 is sine, t. And we do the same thing. We know sine squared plus cosine squared is 1. That means x over 2 squared, sorry, I'll keep them in order. Y over 3 quantity squared plus x over 2 quantity squared is equal to 1. So we've got y squared over 9 plus x squared over 4 equals 1. So what is that? An ellipse. Okay. T goes from 0 to pi. So do we get all of the ellipse? Do we get half of the ellipse? What is it? All right, intuitively, maybe we would think that. What's leading you to think that? Yeah, so notice again, we're still dealing with cosine and sine of 0, ending at cosine sine of pi. If that were a circle, we would say that gives us half a circle. So I think at this point, there's a little room for us to believe that it would be anything but half the ellipse. But what we could do, because it does say graph it, and we could just pick t equals 0, t equals to, pi over 4, pi over 2, 3 pi over 4, and pi, and plot those points. But initially, our initial point would be what? Initial point when t is its starting value, which is here is 0. So we have x equals to 2 cosine 0. And y equals to 3 sine 0. So our initial point is 2, 0. Do y'all remember how to graph that ellipse? No? If you don't remember how to graph the ellipse, then just go off your t values. Initial value, or initial point rather, is 2, 0. And then you just pick some more t's. How about if t is equal to pi over 2, what do we get? We'll do that here. 2 cosine of pi over 2 and 3 sine pi over 2. So when t equals to pi over 2, what point do we get? 0. Okay. So pi over 2, we get the point 0, 3. So we know this is where we start. We know it's an ellipse. At some point, we have to go from here to here, moving in this direction. Yeah, it's centered at 0, 0. Yeah.
Y has, the y value has 9, so no, like the square root of 9, so like my y, but we have to,
Yeah.
X, it's 2 left, 2 right.
Exactly, yep. Yep. So then this other value over here, our terminal point, would be at -2, 0. However many points you want to find in between, it's up to you. But that -2, 0 comes from when t is equal to pi. Stop at 5. Yeah. Okay, so there's our graph. Positive orientation indicated. Half of the ellipse.
What is that?
It is half. Yeah. You know, I guess if you're doing your homework, I recommend you do it by hand, but you can always use this thing to check. 2 cosine 3 squared. Yeah, it is. You get a lot of exotic curves here. So t ranges from 0 to pi. We get half the This is just a circle. Skipping that. You got a very similar procedure here. Just work through this one. If x is equal to t squared, and t is larger than 0, that means the square root of x is equal to t. And we're going to plug that in for y, or into y rather. Y is the ln of t, which is equal to the ln of the square root of x. And by properties of logs, we have 1/2 ln of x. And so that's why our restriction t is greater than 0 because of the y. T has to be greater than 0. But 1/2 ln x, hopefully remember the graph of that. Something to that effect. It's compressed by a factor of 2. So all of these, except for with the sine and cosine, they involve solving for x and 1 of x or y and plugging that into the other one, x or y. With the sines and cosines, we square those to work with that. All right, move. We're now going to talk about derivatives for parametric curves. This plays into the 12.3 when we start looking at derivatives and polar coordinates. Because polar coordinates we're going to think of just as a special case of parametric curves with a parameter of theta. So this extends to other types of systems if we kind of set it up correctly. But what we're looking to describe the derivative, the change in y over the change in x. But we know that y and x are defined in terms of t. So to take the derivative dy over dx, we have to take the derivative of y with respect to t and divide that by the derivative of x with respect to t. So another way we can think about this is the derivative of y with respect to x in a parametric setting is just y prime divided by x prime. The functions of t. And so if we have, another way to see that from the formula, we have dy over dt divided by dx over dt, or times dt over dx. That's just dy over dx because the dt's cancel out. Okay, provided that f prime of t, provided that x prime does not equal 0. For example, x is the square root of t, y is 2t. Find the derivative of the parametric equation and evaluate it at the given value of t. So that says to take the derivative of y with respect to x. We're just going to take the derivative of y and divide it by the derivative of x. So don't get this mixed up with like L'Hopital's rule or a quotient rule. It's really specific to the derivative of y with respect to t divided by the derivative of x with respect to t. Okay, so what is the derivative of y with respect to t? 2. The derivative of x with respect to t? y'all agree? Okay, so there we have our y prime over our x prime. We just simplify that to get the derivative of our parametric representation. We're just going to multiply top and bottom by 2 root t. And it seems kind of weird because we're saying the derivative of y with respect to x is 4 root t. So it's like, we're not accustomed to seeing the derivative of y with respect to x is, like 2x plus 5 or whatever, a function of x. This is a function of t because both x and y are functions of t. Yeah.
Like, no need to ask, but does any of the units, I guess any of the topics of last unit fall into this a little bit, or?
No. But he doesn't. I always thought it was weird in Calc 2 why we did all of this calculus. We paused to seemingly do all of these sequences and series stuff, and then we did some more calculus. And then you see this stuff again when you take like differential equations. So then you take Calc 3, you don't see this sequences and series stuff. Then you get to differential equations and maybe other higher math courses, and you start to see sequences and series come back. And by then, your professor says, oh, hey, y'all remember sequences and series? This is how we solve the differential equation. Okay, we're done. And you're like, wait, what? It was 2 years ago when I saw that. Right? But no, it doesn't. All right, so that says on this parametric equation, to calculate the change in y over the change in x, we just need a t value. Yeah, and so we're given t equals to 4. So sometimes you'll see the notation dy over dx evaluated at t equals 4. I'll change this so we can. Okay, so that just gives us 8. So that 8 is the slope of the tangent line when t is equal to 4. Any questions about that?
Oh, can you repeat what you just said?
So the slope of the tangent line on whatever this parameterization represents is 8, positive 8. So when t is 4 on this original function, we get 0.2, 8. So on this, whatever this represents at the 0.28, the slope of the tangent line is 8. Sorry, I have old slides. So yeah. Yeah, you can bring it up here. Okay. Well. Oh, I wanna. It should have been here. Mad page.
Don't do it. Also, instead of going in a straight line, it's like
kind of like.
All right, sorry about that. It's not in your. I didn't see it in your homework, but I do want to talk about something else for a moment. So this used to be in your homework. I don't see it anymore. So you get a lot of weird curves here. They have weird names too. Consider this, I'm just taking this from an old homework. Consider the, I'll write this word out. Lissa JOUS.
Not done.
Huh. Consider the Lisa Jou. Is that good? Phonetic. So x equals sine of 2t. Y equals to 2 sine of t. And t is in between 0 and 2 pi. And what we want to do is find the points x, y, where there is A, horizontal tangents, and B, vertical tangents. So the point of some of these exercises is to say, like, when we're in parametric equations, all of the traditional rules of calculus that we've studied up to that point are still perfectly applicable. We just have to make sure that we're dealing with the right derivative equation or the integral equation or whatever.
Is horizontal tangent referring to when the tangent of the line is equal to 0?
Correct.
And vertical tangent would just be an asymptote.
Right. Undefined slope, which is vertical, yeah. Okay. So here's the reminder. The derivative of y with respect to x is the derivative of y with respect to t over the derivative of x with respect to t. So let's first think about how we're going to solve a and b independently, and then we'll do that. So here's our derivative. As mentioned, we've got a horizontal tangent when your derivative is equal to 0. So when is our derivative equal to 0? So when is that fraction 0? When the top is 0. So you've got a horizontal tangent when the top dy over dt, which we're calling y prime, is equal to 0. What happens if both dy over dt and dx over dt are 0? Is that quotient 0? No. So we have to be a little bit careful. We have to say we've got a horizontal tangent line when dy over dt is 0, but dx over dt is not 0. How about our vertical tangent?
The opposite.
Yeah. Right. So whenever the denominator dx over dt is 0, our derivative becomes undefined. We got a vertical tangent and the derivative is undefined. So in that formula it said this is your derivative except when x prime is equal to 0, because when x prime is equal to 0 you have an undefined tangent line. It's vertical. and the derivative of, dy over dt cannot be 0. If it comes out that the derivative of y with respect to x is 0 over 0, then we've got to look at L'Hopital's rule to say, is it really undefined? Is it 0? Is it infinity? What is it? We won't encounter that though. So now we know how to find these two things. We need to actually compute y prime over x prime. With respect to t over x prime with respect to t. So y was 2 sine t, which means the derivative of y is 2 cosine t. Yeah, no, this is not in there. You haven't realized that yet. I skipped a page. The last page should be in your notes, but this one is not. And then the derivative of x with respect to t, x was the sine of 2t. So we have 2 cosine of 2t for x prime. So dy over dx is just cosine of t over cosine of 2t. So that's what our derivative, we said we've got a horizontal tangent when cosine is 0. We've got a vertical tangent when cosine of 2t is 0. Yeah, the t ranges from 0 to 2 pi. Did I write that? Yeah, 0 to 2 pi.
Oh, yeah.
All right, so back to part A, horizontal tangent when y prime or dy over dt or cosine of t is equal to 0. It's pretty straightforward there to solve. Here's again a reminder, t is in between 0 and 2 pi. Okay, so when t is pi over 2 and 3 pi over 2, we have a horizontal tangent. Everybody okay with that? Yeah, up to 2 pi, right. And so the instruction said find the points which were x, y. We have the t value at which the two horizontal tangents occur. So the points, point number 1 occurs when t equals to pi over 2. And point number 2 when t is 3 pi over 2. So when t is pi over 2, our x defined as sine of 2t, sine of 2t, y 2 sine of t. Same thing over here. So we're plugging in those t values back into the original parametric equation, so we can come up with the x and y, the points at which these things occur. Is everybody all right with what we're doing there? So this gives us 0, 0. And t equals 3 pi over 2. 0.
Sorry, the first one would be 0, 2.
Is it? Yeah, that's 0 sine of pi. Yeah, sine of pi over 2 is 1 times 2 is 2. 0, 2. And then there's this one. This one's 0, 0. No, that one's sine of 3 pi is 0. negative 2. 0, negative 2. Okay. So 0, 2, and 0, negative 2. I think we'll stop there. Let me just show you the graph, just to kind of solidify that we are on the right track here.
Yeah.
All right, so notice the graph of that curve. And what we said was, here's a horizontal tangent down here at 2, 0, 2, and a horizontal tangent up here at that point, 0, positive 2. Sorry, 0, positive 2, 0, negative 2. So when we find our vertical tangents, how many are there going to be? Just looking at the graph. We have 4 vertical tangents. 1, 2, 3, 4. So we'll, I guess we'll pick back up. What? Yeah, but you gotta remember this curve is generated, point by point, right? As t ranges from here to 2 pi. So if you say this is one line, in a Cartesian sense, that's correct. It's the vertical line x equals to whatever. But in the sense of this parametric equation that was unfolding by t, these are all 4 are determined by different t values. Because it's a different point in time. Think of it like that. It's a different point in time. Okay, so we'll stop there so I can pass out your exams.
Are we gonna do the last example?
Yeah, well, we have to finish this section. We do have to talk about Bartholin.